Okay, so I welcome you all, and I'll be doing an example on the shear stresses in beams, right? So this beam is simply supported and it's built up from three boards nailing together as shown in this figure, and the that's mentioned that the wood has an allowable shear stress of 3 megapascals and determine the maximum value of P which can be taken. That's our first question, and then they ask uh, if the nail can resist a shear force of 1.5 kilonewton, determine the maximum allowable spacing of the nails to support above P, right? So how do we approach this question? So they ask in the first part, they ask the beam fails in shear at 3 megapascals, right? So hence determine the maximum. So in that case, to fail it in shear, right? So a beam like this, to fail it in shear, we need to know where the maximum shear force occurs, right? Where the maximum shear force. So if you draw a shear force diagram to this curve, right? So sorry, to this member, so beam, so it will look like this, right? Is that right? So at the supports, your shear value is critical, right? So you know that if you it's going to be P over 2, right? Okay. So if you have 4P, let's say another 2P, 2P here, P here, P here, then it's all load, total load is 4P, then it's going to be 2P and 2P, right? So that doesn't matter. Whatever we need is we need to find the shear at the support. That's going to be the maximum, right? So shear is critical at the supports, right? So that means that gives you a clue there's a possibility that this beam can fail in shear near the support, right? So we need to know, okay, then they tells us shear stress, right? Not the shear force, right? Then how you approach from shear force to shear stress, right? You know, if the beam is rectangular, right? So this kind of a shear stress distribution along that section, right? So you know at the neutral axis, you have the maximum, right? Maximum shear stress, right? So that means now we came from the shear force to the shear stress, right? So if you have a shear force, let's say shear stress would be tau, let's say uh, dq over I b, right? So this is the shear force, right? So you know, this shear stress becomes maximum at the neutral axis. So that means, okay, now we know at the support, your shear is critical, right? Now we know along the section, what is the critical point, right? So if you draw this beam, right? So your shear would be like this, right? So that means at the neutral axis, right? At the neutral axis, you can't see this, it's into this section. So at the neutral axis, the beam can fail in shear, right? Where your shear stress first reaches 3 megapascal, right? Because this is the highest stress, okay? That means it reaches the failure stress first, right? Let's say this is 10 and this part is 2. Okay? So that means, let's say it fails at 20, So when you increase the load, so this point reaches the failure first, right? So that means if it's going to fail, this point going to fail first, right? Neutral axis fails first, right? So then now we know the point, and we just need to apply this formula, right? So you know the shear stress. So to fail it, right? Tau max, right? So this is the failure stress that needs to fail the beam, right? So if it's not going to fail, so the shear stresses from the load should be what? Should be less than or equal to the shear stress that can take as the maximum, right? So that's going to be VQ over IB, right? VQ over IB, that's going to be, and that tells you this is the shear maximum that can take by the beam, right? It's larger than the shear stress, right? This is the shear stress giving you at the neutral axis, right? Shear stress giving at to the neutral axis. So if our resistance is larger than the available force or the shear stress, our beam is not going to fail. But if it is less than, if it's going so larger than or equal, right? Equal means almost about to fail, right? So now, so we need to know this is 3. This is, I think the value is, yes, 3 megapascal means 3 newtons per millimeter square, right? Megapascals. Oh, 10 to the power 6 newtons per meter squared, right? Okay. So our shear force, so the shear force is, if we apply that P, that's going to be P by 2, right? P by 2. So what's Q? So Q is the first moment of area up to that level, right? From the neutral axis, right? So your neutral axis is now the shear. You know this area is equal to this area, right? Even for this one, right? So that's going to be, so your shear is taken at this neutral axis. So that means you need to take this first moment of area of entire section or the below one. Both are equal, right? So this gives you the Q value. So your Q value would be what? Your Q value can be calculated as sorry, we have to first calculate the I value, right? Yes, since this is an I section, right? So how to calculate the I value? This is your, let's say this is a rectangle. Okay. So the I value is made up from removing these two squares, right? If those squares are all also there, your neutral axis still lies on the x-axis, because above this axis this is symmetric, right? Even if you remove this part or not, so that you can take the I value as I of this square, I of square, remove I of this colored square, right? I of colored square. So that's going to be, anyway, you can take 12 out, right? So what is this value? 25, 25, 200, 25, 100. This is going to be 25, 200, 25, and 25. So the total square is 250. So 250, 200. So that's going to be BD squared 100 into BD cube, right? 100 into 250 cube minus what? Minus that's going to give you these two squares, right? You can sum it up. So the total width is 100 minus 20, 25. That's going to be 75 into width cube. So this will give you I. So we'll calculate it. 1 over 12 into 100, 250 to the power 3 minus 75 into the power 3. That will give you 80 point. So we need, this is in millimeters, you need to convert it to meters, right? So 80.2 into 10 to the power 1, 2, 3, 5, 4, 6 millimeters squared. So you need to convert it to meter, right? So to convert it to meter, you can meter 4, right? You need to, so you have 1 millimeter is equal to 10 to the power minus 3 into meters, right? So that means millimeter 4 is equal to 10 to the power minus 12, right? So you need to multiply it by 10 to the power minus 12. So that's going to give you 80.2 10 to the power minus 6, right? Meter 4. Okay, meter 4. Now my value is okay. Then I need the Q value, right? The first moment of area of this part in red, right? See, this part, right? So the first moment of area is given by Q, right? A y bar. So A is the area and y bar is the distance from the neutral axis to the centroid of this red colored portion, right? Okay. So sorry, is it there? So that's going to give you how much? I think you need to calculate it, right? So the easiest way, because I need this from this axis, so you can take bending moments about that to find the center of gravity. 25, 600. This is also 100, right? Okay, so what you can do is 100 into 25 plus 100 into 25 plus 100 into 25 into moments about this axis. Okay, I'm taking like this. This is the axis. So the entire weight of this is, let's say, at y bar from this. Okay, to y bar is equal to this part separately. So that's going to give you 100 into 25 into this distance. That distance we know, 100 plus 20 plus 12.5, right? 112.5 plus this part into 50. Okay, so I can cut this part, right? So 112.5, I can cut it. So this is going to be 2 times that. So I can 12.5 plus 50. So I can divide it by 2. So that's gonna give you 81 point something, right? So yes, I think it's giving you this 50 plus 160 plus 12.5. Yes, it's giving you something around 162.5 divided by 2 means 81.25 millimeters, right? So now I need to calculate the force, right? So this is okay. Now my V value is, you know that this is a Q value, AY bar, right? So I value, you know, the thickness. Where your shear is getting critical, so you calculate it with respect to this level. So this thickness comes as 0.25 millimeters. So that's going to be 0.25 meters, right? So I value, you know, I value is 18.2 to the power 10 to the power minus 6. So A value, I think you know that too. So it's going to be this part. That is area, total area. That is going to be how much? 5,000 millimeters squared. Millimeter squared means that you have to multiply it by 10 to the power minus 6. Right, so that's going to be 5 into 10 to the power minus 3. So y bar is what? 81.25. So that's going to be 0.08125 meters, right? So that's okay, quite. So I can calculate this part, whole thing together. 10 to the power 3, so 2.8125 over 18.2 into 10 to the power minus 6 into 0.025, right? So that you have to calculate with the and these two as well. Right, so this is going to be how much? This is in meters squared, this is in meters, this is in meters, this is in meter 4. So your answer should be meter squared, so it's going to be meter and meter squared, right? So that's going to be cancelled out with this one. So what's the value? If you calculate it, that will give you. So this would give you 101 times P is less than 10 to the power minus 6 newtons, and P should be less than 29.7 kilonewton. So the maximum value of P, so in order to beam not to fail, P should be less than this value, and the maximum value that P can take is 29.7. Okay. Mathematically, kilonewton. Right. Okay, I think my kilonewton is not visible. Kilonewton. Okay, now great. So then it's okay, right? So maximum value P can take, that's okay. So then they ask if each nail can resist a shear force at 1.5 kilonewton, determine the maximum allowable spacing to the nail support. So this kind of force can take taken by the nail, right? So let's assume a nail like this. So this area will be taken by one nail, right? Actually, it's going to be this area, right? Anyway, that's equal as this one, right? So that's going to be S, right? So if you write an equation, so the total force, right? Total force in this particular area right, let's say F. So that's going to be, you need the shear stress. So this is a stress IB. So this is B, okay? You have to multiply. So you need to convert this to a force. So this area is S into B, right? So then B getting cancelled, right? So BQ over I. What is this? This is called the shear flow, right? So that's going to be F over S, right? So this is the allowable force to a nail, right? Divided by the spacing. So that we can calculate the shear flow of the section at that location. So our beam is like this, right? So that you have nails driven into that, right? So if the nail fails, this will tear and this will separate it, right? If the nail fails, problem due to the shear, right? You know the shear is complementary, right? So if you take a small element, right? If you have shear like this, it will have shear in horizontal as well. So we're probably talking about this complementary shear stress, right? Because if we take a small element, that element is in equilibrium with complementary shear stress. You remember this couple is in equilibrium with this couple. That's how. So this is why the reason most of timber beams fail in horizontal shear, right? So I think their shear capacity in parallel to the grain, so in this direction, is pretty much low. That's why it reaches the failure first, right? Otherwise, this stress is same, right? This is perpendicular to the grain. So this is the shear on this way. If you take this element, okay, think about always the elemental behavior, right? So this will get separated. Right? Initially it was like this. Now it's like this, right? To so that should not occur, right? So that means nail should take that load, right? So likewise, I need to calculate this shear flow, right? So my shear flow is going to be now we're taking because at the interface where it's going to fail, so at this location we should get the shear stress because shear flow, right? So that means the shear force, that's going to be what? If your P is how much? Oh, holy cow, where is P value? Yeah, 29.7. So that divided by 2, right? Because if it is P force, shear force is P over 2, right? So let's say it's around 14 14.8 something, right? 14.85. 14.85 into 10 to the power 3 Newton. Q is this area into, so these are in millimeters. So area into y bar. Y bar is what? 112.5. So these three all in millimeters. So you need to convert it back to meters. So you multiply it by 10 to the power minus 9. 10 to the power minus 3, 10 to the power minus 3, 10 to the power minus 3, right? So that's going to be minus 9. I value you calculated what? 18.2 into 10 to the power 6. right? So this is going to be shear flow 14.85 into 10 to the power 3 by 125 into 12.5, and that's multiplied by 10 to the power minus 9 and divided by 80.2 into 10 to the power minus 6. So that gives you a value of 76. I think it's correct, right? So Newton, millimeter, that's going to area. Okay, millimeter, that's fine. So this is meters. So meter cube, meter 4. Yes, that's giving you newtons per meter, right? Per unit length, right? So per unit length is your F/S, right? So your F value is where your nail can take 1.5 kilonewton. So that's going to be 115 newtons, right? This is newtons per meter. So I'll multiply this by this. So you need to find S. S is given by 1015 divided by 52.6. So that's going to be 0.0428 meters. So it's giving you, let's say, 29 millimeters, right? 29 cannot be measured, so that's probably be, but you can't actually go because 29 is something that cannot be easily measured, right? You have to be practical as well. So that's okay. Mathematically, this answer is okay, but if you keep larger than the spacing, probably your beam will fail, because smaller your spacing, you have more nails to resist shear, right? So that means this is the maximum spacing, right? Then determine the maximum allowable spacing, right? So this is the maximum spacing. That means your spacing should be less than this. So you can practically you can suggest something like 25 millimeters. That's quite okay, right? Rather than 29. Don't you can't go beyond 29, right? So this is very easy, right? So keep these fundamentals in your mind, how a beam fails, right? So let's say something like this. Right? So there you have different nails. There you have horizontal nails up to this, to this. So the similar way, right? So if you need to find, so this can fail with respect to this surface, right? So that means you have to find the shear flow of this at this location, right? So probably you can find the first moment of area of, so you know so you can find shear force. That's easy, child's play. So you know I, you know V. The problem is Q, right? Q is this value, right? So if you need to find this value, so this is going to be these nails divided by that is spacing, let's say it's dash. So if you need to find for these nails, right, so that will fail at this, because that's a connection, right? This built up member is connected from this, right? So for that, you need the first moment of area of this entire portion, right? Okay, so that B is done, Q is then done. I know, so you know that nail can take force, so that might be different spacing. Let's say it's double dash, you can find that, right? That's how you approach to the question, right? This is not about structural analysis. These are fundamentals, right? So yes, I hope you understand. Thank you.